You are at a depth of 8,200 feet, or about 2,500 meters. The pressure around you is 250 atmospheres. The water temperature is 39 degrees Fahrenheit, which is about 4 degrees Celsius. Not a single photon of light exists here, not because your equipment failed, but because physics does not allow light to reach this depth. This is a silence unlike any silence you have ever experienced. It is not the absence of sound. It is a pressure with physical weight, pressing down on everything, suppressing everything, including yourself. There are no currents. There are no biological sounds. There is nothing. There is only darkness, pressure, and you. Then, with no warning, no sign, no prior sound, something fires right next to you. You do not hear it. You feel it, like a physical blow to the middle of your sternum, piercing through your chest, spreading to every part of your body in less than 1/100th of a second. 230 decibels. A jet engine at full throttle produces 140 decibels. This is not just a sound that is 90 decibels louder. On a logarithmic scale, this is a sound that is 1 billion times greater in energy intensity. And 66 feet ahead of you, or approximately 20 meters in total darkness, something is waiting. It is not waiting to escape. It is waiting to see what those 230 decibels just did to its target, whether it worked or not. This is what the record shows. Physeter macrocephalus, the sperm whale, is the largest toothed animal alive on Earth. An adult male can reach 59 feet, which is about 18 meters, and weighs 63 tons, or approximately 57 metric tons. It possesses the largest brain of any creature that has ever existed on this planet, weighing more than 17.6 pounds, which is about 8 kilograms, and every day it dives down 6,500 to 9,800 feet, or about 2,000 to 3,000 meters, into total darkness to hunt. The sperm whale is a mammal. It breathes with lungs. With every dive, it carries a fixed amount of oxygen, and it must complete its hunt, eat enough of what it needs, and then return to the surface within about 90 minutes using that single supply of oxygen. At 8,200 feet, which is about 2,500 meters, its eyes are not effective. Its prey, the giant squid and the colossal squid, are fast reacting, soft-bodied creatures with no bone structure, capable of disappearing into the darkness in a few hundredths of a second. Theoretically, this is the most difficult type of prey to hunt using any conventional physical method. Yet, the stomachs of sperm whales are full of squid, hundreds of squid every day. The question is not what it eats. The question is why an animal needs 230 decibels to do it, and whether 230 decibels is truly just a tool for navigation, or if it is something else entirely. But that is only the first problem. This is what the record shows. The accepted model for decades is that sperm whales hunt using biosonar, the same basic principle used by bats and dolphins. The spermaceti organ in its head produces a series of clicks. That sound passes through the melon, a special fatty structure, and then radiates forward into the water. The clicks bounce off the prey. The sperm whale listens for the echo. From the return time of the echo and its angle, it builds an acoustic map of its surroundings in total darkness. This is a clean framework, intuitive, easy to visualize, and it is correct, partially. Bats use biosonar at around 100 to 120 decibels. Dolphins use 120 to 130 decibels. These are power levels appropriate for the task, strong enough for the sound to reach the prey, bounce back, and be detected before fading out. The physics of echolocation do not require anything more than that. To locate a squid at 164 feet in the water, which is about 50 meters, acoustic calculations show that 150 to 160 decibels is sufficient with a wide margin of safety. The sperm whale is producing a sound that is 70 to 80 decibels louder than necessary for navigation. On a logarithmic scale, an excess of 80 decibels is not just slightly louder than necessary. That is an excess of acoustic energy 100 million times greater than pure navigation requires. This is what the pure biosonar model fails to explain. If the sole purpose of the click is to receive an echo, why did evolution invest in creating a sound hundreds of millions of times more energetic than necessary? Each 230 decibel click consumes oxygen, the single thing that limits dive time. An animal at 8,200 feet, or approximately 2,500 meters, with a fixed amount of oxygen does not waste energy unreasonably. Evolution does not retain what has no function. If 160 decibels is enough to navigate, 230 decibels is doing something else. The acoustic stun hypothesis was first seriously introduced in scientific literature in the 1980s. The idea is not complicated. The 230 decibel click does not just locate the prey, it attacks the prey. The sound is powerful enough, in a water environment, and focused enough to cause temporary neurological disruption. It is enough to immobilize the prey for a few crucial seconds. And this is where the data begins to become unusual. The decibel scale is logarithmic, not linear. Every 10 decibel increase is equivalent to a tenfold increase in intensity. Comparing 230 decibels to 140 decibels, a 90 decibel difference means the acoustic energy intensity is 10 to the power of 9 greater, 1 billion times. In the air, this would already be extraordinary, but sound in water travels 4.5 times faster than in air and carries energy in a way that is non-linear with speed. Underwater, at close range, 230 decibels is not just a sound. It is a physical force that can be felt as mechanical pressure acting directly on biological tissue. Experiments with fish in controlled environments have shown that underwater sound at levels of 180 to 200 decibels causes temporary acoustic stunning, disorientation, loss of motor coordination, and, in some cases, brief unconsciousness. This is not a hypothesis. These are results that have been measured, documented, peer-reviewed, and replicated multiple times. The threshold for causing temporary neurological disruption in vertebrates lies significantly lower than 230 decibels. The sperm whale is operating at a level 30 to 50 decibels higher than the documented threshold, equivalent to thousands to millions of times the intensity required to cause stunning. But that is only the first problem. The primary prey of the sperm whale, the giant squid Architeuthis and the colossal squid Mesenacateuthis, have a specific anatomical structure that is extremely sensitive to changes in acoustic pressure, statocysts. These are organs that sense gravity and acceleration, the equivalent of the vestibular system in vertebrates. The statocysts of squid are incredibly sensitive to rapid and intense pressure changes. A large enough acoustic pulse acting directly on the statocyst can cause complete disorientation. The squid does not know which way is up or down and cannot trigger its escape reflex. This is not an injury. This is a temporary system failure. It is enough for a 63-ton animal, which is about 57 metric tons, to approach and swallow it before it recovers. Stomach analysis of examined sperm whales has shown an unusual pattern. A significant percentage of squid mantles were found relatively intact, not bitten, not torn, with no signs of an active chase and attack. This is inconsistent with a 63-ton animal, which is about 57 metric tons, biting its prey to death in the dark. It is more consistent with prey that was already immobilized when swallowed, and the teeth of the sperm whale are not designed for chasing. They wear down in a pattern that is incompatible with catching fast-moving prey. Anatomical evidence does not support the chase and bite model. Physics does not rule out the acoustic stun hypothesis. The anatomy of the prey does not rule it out. Evidence from the stomach does not rule it out, but there is no direct evidence. No one has observed a complete hunt at this depth. Everything is an inference from fragments. Science does not have an answer to this, not yet. This is what has been recorded. When hydrophones track a sperm whale during its hunting phase, a distinctive acoustic change occurs as it approaches the final attack stage. The click rate accelerates abruptly from a few clicks per second to hundreds of clicks per second, creating a continuous sound that researchers call a creak. This pattern is completely different from normal navigation clicks. It appears consistently in every recording at the stage where the animal is believed to be approaching its prey. This has been clearly documented, but its exact meaning, whether it is a final burst of acoustic energy aimed at the prey, or an increased echolocation resolution for more precise tracking, has not been determined. There is one data point that no one can explain satisfactorily: the giant squid, the primary prey of the sperm whale through millions of years of evolution, has no observable acoustic defense mechanism. If the sperm whale has been using sound as a weapon continuously for millions of years, the evolutionary pressure on the prey to develop a countermeasure should be immense. Absence of evidence is not evidence of absence. However, this is an unusual gap in a predator-prey relationship that has lasted long enough to produce complex coevolution in many other traits. Producing a 230 decibel click costs significant energy and costs oxygen. During a 90-minute dive, a sperm whale can produce thousands of clicks. The oxygen allocated to those clicks is oxygen not allocated to maintaining organ function or muscle movement. If 160 decibels is enough for navigation, 230 decibels is an extremely expensive evolutionary decision. Evolution does not retain costly decisions if they do not return a proportional benefit. What that benefit is has not been directly measured. Every study on sperm whales ends at the same limit. We cannot observe the hunt at the depth where it actually occurs. Remotely operated vehicles cannot keep up. Hydrophones record the sound but do not record the result. The best evidence we have of how sperm whales actually hunt is the stomach contents of dead animals and the scars on their skin from battles with squid that no one witnessed. As of the most recently recorded expedition, it remains unknown. This might be showing us something else entirely. The spermaceti organ does not just produce hunting clicks. It also produces codas, complex click patterns that sperm whales use to communicate with each other. Studies on codas have confirmed that different family groups have distinct dialects. The coda pattern of one group is unlike that of any other group. The exact same physical organ, the exact same acoustic mechanism, generates both a signal that can stun prey and a language that can transmit cultural information from mother to child. We are describing an animal that uses the same body part to both stay in touch with its family and potentially attack its prey from a distance, in total darkness, at depths that none of our equipment can fully track. The 17.6-pound brain, which is about 8 kilograms, of the sperm whale is not large by accident. Its neocortex, the part involved in complex information processing, learning, and social cognition, has a larger surface area than that of any animal studied. If the acoustic stun is a learned skill that is refined through experience, not a pure reflex, then this brain has more than enough capacity to do it. Some researchers have questioned whether there might be group coordination, multiple sperm whales firing from different angles to maximize acoustic pressure on the same target. That question remains unanswered, but the fact that the question is even raised speaks volumes about this animal. We are talking about an animal with the largest brain in the history of life on Earth, a language complex enough to carry regional dialects, that dives down 8,200 feet, which is about 2,500 meters, into total darkness and might. According to evidence that physics does not rule out, be using sound as an active weapon, and we have known about its existence for centuries, have hunted it to the brink of extinction, and still do not know the most basic thing about how it feeds. Less than 20% of the ocean floor has been directly observed. Every day, sperm whales are diving into parts of the ocean that none of our instruments can follow. Every day, 230 decibels are being fired in the dark, aimed at things we have never seen, by an intelligence we do not understand. Those hunts were happening tens of millions of years before we existed, and they will continue to happen long after we stop looking. There is one final thing that the record shows. A 230 decibel click fired at 8,200 feet, which is about 2,500 meters, does not stop at the prey. It continues to travel through the ocean, not fully absorbed, until it finally fades out after thousands of miles, or approximately thousands of kilometers. Hydrophone stations around the world record sperm whale clicks from halfway across the globe. Right now, while you are here, the ocean is full of those signals. Hundreds of animals are firing simultaneously in the dark at things we cannot see, and we do not know why they need to be so powerful. The documentation of what is happening in that darkness continues to accumulate, slowly, one expedition at a time, if you want to follow what is being recorded as it is recorded. The archive is open. The deep still has so much more to show you.